In this next section of Lesson 21, we're going to talk about charging by induction and inducing charge to move on conductors and in insulators. Let's start by talking about the charge on conductors. Since conductors are objects on which charge can easily move, then it stands to reason, and it's found experimentally to be true, that if there is an excess amount of charge on the conductors, then the charge arranges itself in such a way to try to be as far apart from other charges as is possible. Now, we're going to see in later lessons that the shape of the conductor will greatly influence the way that the charge arranges itself, and we'll see that sharp edges of a conductor will be a place where excess charge tends to reside. That's the reason lightning rods tend to be sharp. But nevertheless, what happens is that the charge tries to rearrange itself so that it's as far apart from the other charges as possible, which means that the excess charge on conductors is on the surface of the conductor. In this lesson, we're going to focus on spherically shaped conductors so that essentially the radius of curvature of the surface of the conductor is the same everywhere, and in later lessons we'll then allow that radius of curvature to vary so that a sharp area on the surface of a conductor would be represented by a very small radius of curvature. That's where the charge is going to pile up. But nevertheless, if I had a spherical conductor and I had a bunch of excess electrons that I dump onto the conductor, then the electrons are going to be found at the surface. So here I've sketched a spherically shaped conductor, and now I'm going to dump some excess charge and arrange it so that it's evenly spaced along the edge of the conductor. So these excess negative charges are evenly spaced along the surface of the conductor. I don't like your textbook's diagrams of their spherical conductors because I don't see them arranging the charge evenly along the surface. But on a conductor, that's where the charge is. Likewise, if there's a deficiency of electrons, if the conductor is positively charged, then we would see that the electrons would rearrange themselves in such a way that there would be an absence of electrons along the surface of the conductor, and you would see that that surface is positively charged. So I'll draw another sphere on the other side of the page to represent that. Let's talk for a moment about excess charge on insulators. Because charge is not free to move on an insulator, then what we find is that wherever the excess charge happens to be on the insulator, the excess charge is going to tend to stay on that spot of the insulator. It's possible for the charge maybe to move a little bit, but it's not going to shift from atom to atom as the excess charge would on a conductor. So basically, the excess charge is confined to the area of the atom that it's associated with on the insulator. So it's possible for one side of the insulator to be charged and another part of the insulator to be neutral, so that the whole insulator will have an excess charge, but the charge is not free to move around on the insulator like it is on the conductor. That's not as easy to depict graphically as the excess charge on a conductor, and so I'm not going to try to do that in a diagram. But nevertheless, most of the kinds of problems you're going to see, at least in these early lessons, are going to be dealing with charges that are on conductors. And so for those purposes, those charges are going to be located at the surface. The excess charge is going to gather on the surface of the conductor. Let's talk about inducing excess charge to appear on a conductor. And in order to do that, we've got to have a charged object and an initially neutral object. So what we're going to discuss now is charging by induction, the third method of having charge show up on an object. This is a multi-step process that involves inducing a charge separation on the neutral object by the presence of a charged object. That's going to be the first step, and in fact that's where the charging by induction comes from, because I'm inducing a charge separation. The second step is going to involve attaching a third object, usually a ground or a source or sink for electrons, to the neutral object so that excess electrons can either move onto or off of the initially neutral object. And then the third step, if we want to have excess charge remain on the initially neutral object, is to disconnect that ground. Let's illustrate what we're talking about. Let's begin with a conductor that's spherically shaped, and initially it is a neutral object. And let's bring up close to this neutral object a positively charged wand. Maybe it's a piece of glass that's been rubbed by silk. It is a charged object that's positive. As this charged object approaches this conductor, then there is a polarization that occurs with the electrons on the conductor tending to migrate over towards the positive wand, leaving behind the positive charges that can't move. Those positive atoms, maybe on the right side over there, get stripped essentially of their electrons. The neutral object is still neutral, but it is polarized because there's a charge separation that is induced. So you could call this first step a polarization step. Again, this initially neutral object is still neutral, but it's polarized. The next step in this process is to provide some object that can give or receive excess electrons and attach it by a conductor to this polarized object. We call that grounding the conductor. So I'm going to take and attach a ground wire, and the symbol is a conductor that's attached to something that's buried in the ground. Those lines indicate a sharp point that's somehow buried into the ground. And the ground, it turns out, is a pretty good conductor, and it's so large compared to these other objects that it can give or take electrons without really changing its charge state very much. Well, this ground wire allows conduction of electrons. This side of the sphere that's polarized attracts electrons from the ground. So I get some electrons leave the ground and come on to this sphere as long as that positively charged wand is present. Now, electrons are electrons, but I have, just for clarification purposes, drawn some electrons red, the ones that were originally on the conductor, and others that are black, ones that come from the ground. So now some electrons move from the ground onto the polarized conductor, and so I end up with more electrons on the conductor than I had before I put the polarizing positively charged wand in place. That's the second step. Now the third step is to remove the ground in the presence of this polarizing wand so that the electrons that came up from the ground are stuck on the polarized object. So what happens is, in the presence of this polarizing rod, I disconnect the ground from the conductor. And whatever charges moved in the process while the ground was connected, those charges are stuck. Now in this case, we had electrons come up onto the sphere, and those charges now don't have a path to get back down to the ground. Now, of course, if I were to remove the polarizing rod before I remove the ground, those charges that came up onto the conductor are going to go back down onto the ground so that the sphere would be neutral. But I do this breaking of the ground in the presence of this charging wand. Now, let's notice that the final charge state of the conductor is opposite to the sign of the wand that was doing the charges. That's a characteristic of charging by induction. The sign of the charge on the neutral object is opposite the sign that was on the charging object. Let's repeat the diagram, but this time use an initially negative wand. So here I have a polarized sphere. It's initially neutral in the presence of a negatively charged wand. And because the charges are free to move on the surface of the sphere, because it's a conductor, then the electrons are driven away. They're repelled by this negative wand. That's the polarization step. Next comes the grounding step. Now I connect the ground. Electrons leave the polarized sphere because they want to get as far away as possible from this negatively charged wand that's doing the polarizing. So they leave the sphere and they go on to the ground. Next, I break the ground. I remove the ground. When the ground is broken, those electrons that departed from the conductor are stuck on the ground. And now I've got a deficiency of electrons, an excess of protons, and so the final state of this initially neutral conductor is opposite in sign. It's positive compared to the negative wand that was doing the charging. That's the process of charging by induction.